9 out of 10. We're so close. We are so close. So close. So up here in blue, right around here, right, this little bit, these were the conclusions from the last video, video 8 of 10, the functions for relative cardinality. In this video, we're going to talk about these definitions. So I'm just going to say what they are right now. A set A is countable when its cardinality is no larger than the size of the natural numbers. A set A is infinitely countable when it's equal. Okay, so as a first corollary, right, we would hope every finite set is countable. That's terrible handwriting. Oh my word. Okay, so this is true. This is a theorem. I'm going to give you two quick examples. Let's first show that bool is countable. Okay, so how would we prove this theorem? Well, the result that we need is this, right? That the cardinality of bool will be less than or equal to gnat. How do you show that? Well, we have two options, right? We could either come up with an injective function from the bools to the gnats, or we come up with a surjective function from the gnats to the bools. I'll quickly do both for you. Proof by injectivity. Okay, so let f bool arrow gnat be f of true equals 0, f of false equals 1. F is injective. Right? Clear enough, right? 0 doesn't equal 1. So the cardinality of bool is less than or equal to the cardinality of gnat. Okay, here's a different proof. Proof by surjection. Let f be a function from gnat arrow bool be f of 0 equals false, f of n, or let's be super clear, s of n prime be equal to true. F is surjective, right? F of 1 equals true. F of 0 equals false. So the cardinality of bool is less than or equal to the cardinality of n. Okay, from this you should hopefully see that there's just kind of a recipe for coming up with this function for finite numbers. You have a choice. Every time you do a proof of relative size, you have a choice. Do you want to do it via injection or you want to do it via surjection? And everybody finds that they're like a kind of person. Like maybe you're really injecty as a person, or maybe you're really surjecty as a person, and that's totally fine. Either way you do that is up to you. Sometimes one is easier than the other, so I recommend flexibility here. Like if you can do it both by injection and surjection, I think you'll be happier. But if there's one, there ought to be the other, though sometimes it's much less comfortable. Okay, cool. So that's for finite sets. That's really not so interesting. So I want to, that's unfair. That's not the most interesting. The most interesting is infinite countability. So let's think about that. There's a couple of sets I want to look at. So one of them is the set n plus, which are, those n are greater than 0. This is also known as positive numbers. Right? Some mathematicians would call this the naturals, and I would say politely that this is my class, and why don't you go teach that in your own class? Okay, so that's the positives. There's also z, the ints. You might wonder why it's a z, and it comes from German Zahlen, which is to count, which is also how you ask for the bill. But confusingly, you actually don't count with the negative numbers, so the whole thing's very confused to me. But anyway, the integers, we'll want to talk about them. I want to talk about pairs of naturals, and then I want to talk about the rationals. all of these sets are infinitely countable. Just like as a spoiler alert. I.e., have the same cardinality as the naturals. So that might not be so surprising for the positives. I mean, you're missing one, so that's weird. Maybe surprising for the integers, and probably very surprising for these two, for the pairs of naturals and the rationals. So I'm going to try to go through each one slowly, which means this video isn't going to be the absolute shortest possible, but I'm hopeful that this will sort of give you all the tools you need to think clearly about this and do the homework. Okay, so let's start with the theorem n plus is infinitely countable. The positives are infinitely countable. Okay. Proof by allegory. And then we'll do a real proof. So the big universal math conference is having a conference on Betelgeuse, however you pronounce that star. Betelgeuse. So they're having their conference, and infinitely many mathematicians are going to come up, like one for each of the naturals. So that's fine, and all the rooms in the hotel need to be filled. So we have all the rooms. Right? There's room 0, there's room 1, room 2. Right, and there's a mathematician from planet 1 or planet 0, planet 1, and each of them just sort of get assigned to their appropriate room. 2, planet 3. But then, because of COVID-19 quarantine restrictions, Earth, planet 0, can't make it. So the conference organizers get worried because, like, look, we have a contract with this conference. We have to this hotel. We have to fill all the rooms. So what are we going to do, right? Because planet 0 can't make it. So what's everybody going to do? So they say, oh, well, look, I know there's infinitely many rooms here, but what we'll do is let's just have everybody shift down a room, right? Planet 1 can stay in room 0, and planet 2 can stay in room 1, and planet 3 can stay in room 2, and so on, right? And then still all the rooms will be filled because we've got infinitely many mathematicians, so no one will miss the fact that Earth doesn't come, though of course we'll all be sad to miss the earthly contributions to the Universal Math Conference. So the hotel is still filled and the contract is held up. Okay. What? So, how does that work? Proof for real. What we need to do, so we need to show a bijection between the positives and the naturals. So let f be a function from the positives to the naturals. We must show it's bijective. Okay, so let me define f. So f of n, and really we can write f of s of n, right? Because it's always going to be the successor of something. The answer is just going to be n. It's just going to be one number less. This is the room shifting we just saw there. F injective. Yep. S of n does not equal n for any n. So every input will give a different output. Is it surjective? Yep. F inverse of n equals S of n. Right, so, well, that's maybe not the most useful thing to say at this point. I apologize. Why is it surjective? To hit m in n, pick n equals S of m in n plus. Right, and we know because of that successor, it'll always be a positive number. It won't be 0, so we're sort of lined up. Okay, so that's the proof. Okay, there's another simpler way to do this proof. If A is infinite, and the cardinality of A is less than or equal to the cardinality of n, then the cardinality of A equals the cardinality of n. Right? This is a shorthand. Oops. All right, so why is that? Well, if it's already infinite, that means it has to be at least as big as the natural numbers. Why? The general understanding is n is the smallest infinity. So let's do this proof one more time in a different way. Proof simpler. N plus is infinite. So it suffices to show that the cardinality of n plus, the positives, is less than or equal to n to find the cardinality of n plus equals n. So what that means is we really only need to show one side, right? We need to show one of these two. Either we can come up with a surjective function from the gnats to the positives, or an injective function from the positives to the gnats. Just to mix things up, let me do the surjective function. So here's a simpler proof. Let g from gnat to gnat plus be g of n equals s of n. Observe that g is surjective. So the cardinality of n plus is less than or equal to the cardinality of n. Nice. Simple. You can also do it with an injection from n plus to n. In fact, you would just probably choose the same f we had over there. Okay, cool. So, 1 down, 3 to go. Theorem. The integers are countable. Proof by allegory. Okay, same hotel. This hotel has a name. I didn't come up with this allegory. It's called the Hilbert Hotel, named after the mathematician David Hilbert. David Hilbert was to math as I think Elon Musk is to tech dorks today, except for he was actually really competent and really talented, whereas Elon Musk is, I think, really mostly just rich. David Hilbert was just like the man for mathematics. I really recommend you look him up. He's just got an incredibly cool story, and then he came up with these sort of like epochal century problems called Hilbert's problems that he set the agenda for mathematics in the 20th century. He is a BFD. Yes. Okay, so the Hilbert Hotel, they're doing the next run of the Universal Math Conference, and this time they have a different problem. Every planet has decided to send not one professor, but two, and they each want their own hotel room. Professors, am I right? Totally unwilling to share. So they have this problem where, like, okay, we had room 0, we had room 1, we had room 2, we had room 3, and someone from P1 was assigned to room 0, and someone from P0 was assigned to room 0, P1 to room 1, P2 to room 2, P3 to room 3. But double? We have infinitely many people coming, and now you're telling me we have twice as many coming? Because now we have a P0 prime. Well, let me get a good color for this other one. Yeah. We have a P0 prime and a P1 prime and a P2 prime and a P3 prime. Where are we going to put all these people? What are we going to do? Because now the conference managers feel fine because the hotel has this contract to let everybody in, but the hotel people are panicking. Where are we going to put everybody? Right? We have twice as many people as we thought. And then one of the people has a really good idea. They say, well, you know what we're going to do? Let's just tell everyone, look, you've got a certain room number on your room key. Come to the front desk, and we'll put you in a room that's double that number. So if you were in room 0, you don't have to move anywhere. But whoever's in room 1, you're going to be in room 2. Whoever's in room 2, you're going to be in room 4. Let me draw room 4 just so it's a little clearer. in black, please. In room 4. And whoever's in room 3, okay, you're going to be in room 6, and so on. And great, so now everyone in these new rooms, well, they can just go to all of the odd rooms because they're unaffected. So if you're in room, if you're from planet I, you'll go to planet 2 times I plus 1. So the next person from P, the extra person from Earth will go to room 1. Let me draw that in. Whoop. Yes, I know I'm in Microsoft Whiteboard. Thank you. You'll go to room 1, you'll go to room 3, you'll go to room 5, you'll go to room 7, and so on. We'll just sort of squeeze them all in between, right? And that way they have enough room for everybody. Okay, what? Okay, so we have a choice. We now need to, proof like for real. We have to choose to do it by injection or by surjection. So I'm going to do it by injection. So we want a function f from integers to naturals. Injective. Then the cardinality of the integers will be less than or equal to the cardinality of the naturals. But the integers are infinite. Okay. Okay, so we need to just come up with this injective function. Okay, so what are we going to do? So f of some number, I'll call it x to remind us that this is an integer, not just a natural number. So what are we going to do with it? So I'm going to break the cases up and say, like, look, either x is greater than or equal to 0, and then you're going to go to room 2x. Or, otherwise, might as well write that out. It'll go to negative 2x plus 1. Okay. Why is f injective? Either x greater than or equal to 0 and f of x is even, or x is strictly less than 0 and f of x is odd. Right? Another thing you want to definitely verify is, look. Look. Are we sure that that's a natural number? Think about it. It is, but it took some complicated math. There's a reason we're doing this informally and not in Coq. Okay, but anyway, this argument is enough to show that f is injective. So that covers the proof. Let's do it with a surjective function. So what do we need? We want f from the naturals to the integers surjective. This is a little harder to see, but what I'm going to do is I'm going to use the trick that the inverse of an injective function is a surjective one. And in fact, here f is a bijection. It turns out. You can check that if you like. But so here I'll just write it down. So g of n is equal to, all right, so if n is even, I'll do n over 2. If n is odd, then what will it be? N minus 1 over negative 2. So g, did I get that right? No. What am I doing wrong? N plus 1 over negative 2. So let's see. G of 0 is going to be 0 over 2 equals 0. G of 1 is going to be 2 over negative 2 equals negative 1. G of 2 is going to be equal to 2 over 2 equals 1. G of 3 is going to be, let's see, 3 plus 1 over 2 over negative 2. So that should be negative 2. That's 4 over negative 2. G of 4 Okay, that should just be 4 over 2. Okay, so that's 2. Okay, so if you like, you can see that G here maps hotel rooms to guests, and F here maps guests to hotel rooms. Okay, so 2 different ways to do this proof. Okay, cool. Halfway there. 2 more proofs. Theorem. The product of the gnats are infinitely countable. Whoops, doopsie. Okay, this to me is one of the more mind-blowing facts in all of this mathematics. The naturals, there's infinitely many of them, and I'm telling you there's just as many as if you have 2 naturals as if you have 1 natural. This is so counterintuitive, so unexpected, and once you see it, so obviously true and such a powerful fact that it's really just like a perspective shift. I think it's really, really cool that once you get this, you just see infinity differently. Are you ready? Are you ready to have your world changed? Okay, I'm going to give you the intuition. So you have to be careful about how you set up the numbering. Any countability, so when we say something like this, if we come up with a surjective function, f from the gnats to pairs of gnats surjective, that'll do it. But we need to do it. So what that amounts to is some sort of numbering. So that what is that going to look like? That looks like 0, 1, 2, 3, and it's going to be n1, n2, or here, let's think of it differently. Boop, 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 boop. You'll have n01, n02, n11, n12, n21, n22, n31, n32, and so on. This seems so unlikely, right? Like there's so clearly fewer things on the left than there are on the right. How will you ever do it? So I'm going to draw you a picture, and it's going to show you how you do it. Okay, so let's think about what we really want. Let's do a different color, sorry. So here's the start. So this is 0, 0. One, 2, 3, 4. And imagine this bit going on infinitely. If you like, you can think of it. Oh, that's not quite spaced enough. If you like, you can think of this as one of the quadrants of the Cartesian plane. Okay, and then we're also going to have points, intermediate points, that correspond to each of these. So if you think about it, this grid, if you extend it infinitely, wait, what am I doing? There we go, thank you. Right, this grid, if you extend it infinitely in every direction, this covers all of the possible pairs. Right? There's n times n. Okay, so what I'm going to show you now is that we can find a path through this that gives us a number. Right, so here's 0, 1, 2. And then we'll just zigzag. 3, 4, 5, 6, 7, 8, 9. Okay, and then here we're at 10, 11, 12, 13, 14. Oh, excuse me, that's not. And then the next line will go off this way. right? And then what we'll do is we'll just keep zigzagging like this. So because we have these boundaries here, oops, let's redo that. Because we have these boundaries here and here, we know that this zigzag, let me write it down, the red path hits every dot. So we count every pair in n times n. Okay, one thing that Gerrit did was he sort of formalized this, right? You can write down this path as a function. It is, needless to say, a little bit annoying, but you can totally do it. It's called the contour pairing function, and it just takes some thinking to set it up right. I'm not going to write it down here because the details aren't important. What's important is the recognition that we just collapsed two infinities into one. Right? So what is that? What do I mean by that? We just found that the cardinality of n times n is less than or equal to the cardinality of n. So in particular, they must be equal. Whoa. This doing it every time, this blows my mind that it works this way. Once you see it, it feels so obvious, and before then it feels so impossible. It's really an amazing feeling. I think you should relish the moment when it clicks as sort of this is a shift in how you see the world. Okay, one last one to look at. It's really just a corollary of what we just did, right? The rationals. Why doesn't it change color? If anybody knows anything about this program, I'd love to figure out why that doesn't always happen. Theorem. The cardinality of the rationals is equal to the cardinality of the gnats. That is, the rationals are infinitely countable. Proof idea. Here's a function, f from n times n to q. F of n1, n2 equals n1 over n2 when n2 is not equal to 0 and 0 otherwise. Okay? F is injective. So that means the cardinality of n times n is no larger than the cardinality of q, of the rationals. F is also surjective. Right? Every rational can be formed as the fraction of two numbers. In fact, f hits a bunch of extra numbers. So this injective is actually, this is not correct. It is not injective. Because, for example, f of 2, 2 equals f of 4, 4. So sorry about that. F is not injective. My mistake. F is, however, surjective. Right? Which means the cardinality of the rationals is less than or equal to the cardinality of nat times nat. But that's less than or equal to the cardinality of nat. Since the rationals are infinite, they must be the same size as the naturals. Okay, really sorry about that confusion. Just got carried away with myself. Hopefully that's all cleared up. This is not quite a rigorous proof. I think an account that you'll often see will be to reproduce the same matrix that we saw over here for the pairs of numbers to talk about the rationals. And then sort of people will wave their hands to say like, oh yes, and there's this whole issue about like, fractions that are multiply representable and things like that. And it's really not that important. It's like, okay, well, it's not trivial, but indeed, that is the general proof idea. Okay, to sum up. Oh, where'd we go? Oh no, I lost it. ET phone home. To sum up. Whew. Thought I'd lost it forever. You can tell I'm making these videos at the end of the day, huh? To sum up, what have we learned? Please stop. We defined countability as the relation of a set to the naturals. And then we saw 4 surprising facts. That the naturals are the same size as something smaller. Adding or removing a finite number of things leaves something in the same cardinality if it's infinite. Doubling the set left us the same, right? Just like in terms of laying the numbers on the line and then having all of the negatives also. But then not only that, taking the pairs, this Cartesian product of the set, that kept the cardinality the same. So surprisingly, that let us conclude that there are just as many natural numbers as there are fractions. Mind-boggling. Absolutely insane. Nobody saw this coming. When Georg Cantor came up with this and first came out with these proofs, the correct term for how people reacted was shitstorm. People freaked out. So anyway, I hope you're not as freaked out as mathematicians were about 130 years ago when Georg Cantor first made these discoveries. Excuse me, even earlier than that, 140, 150 maybe. I hope it made sense. If you have questions, please post them on Piazza. Check out the homework. You're already at this point able to do a huge chunk of it. Okay, take care, everybody.